Two-column proofs. How to avoid confusing converse and inverse. Imagine trying to solve a puzzle where pieces look similar but fit differently. That's what confusing the converse and inverse in geometric proofs can feel like. Let's clear that up so your proofs stay sharp and correct. First, understand that a conditional statement is like a simple rule. If P, then Q, for example. If a figure is a square, then it has for right angles. The converse flips this around, making it if Q, then P, which would be if a figure has for right angles, then it is a square. The inverse, on the other hand, negates both parts, turning it into if not P, then not Q, or if a figure is not a square, then it does not have for right angles. The tricky part is that the original statement, the converse, and the inverse can all be true or false independently. Just because the original is true does not mean the converse or inverse are true. For example, many rectangles have for right angles, so the statement, if a figure is a square, then it has for right angles is true. But the converse, if a figure has for right angles, then it is a square, is false because rectangles also have for right angles but are not squares. When working with two-column proofs, it's essential to write down the original conditional clearly in the statement's column. Then, if you need to prove the converse or the inverse, label each one carefully. For example, write converse of the original statement next to the step where you address the flipped condition. This helps keep your reasoning organized and prevents mixing up the logical forms. Remember, proving the converse or inverse isn't automatic. Each one needs its own proof or justification. Do not assume that because the original statement is true, the converse or inverse are automatically true. Use specific reasons like by definition of the converse or contrapositive of the original to explain each step. Practicing with examples helps too. Take the statement, if a figure is a triangle, then it has three sides. The converse is if a figure has three sides, then it is a triangle, which is true. But if you change it to if a figure is not a triangle, then it does not have three sides. That is the inverse, and it is also true. Recognizing these differences makes your proofs clearer and more accurate. Finally, always focus on the logical flow. Each step should follow from the previous one with a valid reason. Avoid assumptions based on confusing the converse with the inverse. By clearly marking which form you are working with and proving each separately, your proofs stay correct and easy to follow. This way, you can confidently navigate advanced geometric systems and create proofs that are both precise and understandable.